Hey, hi, good evening to all. Um, yeah, so I would like to discuss a few important things before moving on to addressing your queries. Let me discuss this first. Um, Let me share the screen. Okay. Okay. So often, so what I see among the students is that they struggle a lot to understand the indexes. Okay. So when you can see that throughout the deep learning all the computation involves kind of matrix vector product, nothing beyond that. But the thing is that we just extend it to tensor, not just to columns and rows, depth as well. So while we do so, since we have at least some 4 to 5 dimensions involved, especially when you implement something in PyTorch or in any other framework, it is essential to understand each dimensions and understand also the formulas involved in computing something. So here you can see a very some formula, right? So it is not necessarily related to deep learning. It is just some expression. Okay, so by just looking at this expression, of course, it's very difficult to exactly tell you what this expression is computing. We can generalize this. Okay, so here we have some x, y, and c, and then of course there is some nebula operator before x. But in general, right? So we can simply generalize this. Okay. Once again, now I have a same expression, but with it, it does something different. Okay, now I have functions, and here it's simple multiplication of something, right? Can you tell me what exactly is happening here in this expression? Yeah, take your time. Just look at the indices and try to map it in your mind, and can you at least guess what is going on here? Because the expression could get complicated. I can do whatever the operations involved, but you just take a look at the third expression. What are we doing here?
So result matrix multiplication.
Okay, matrix multiplication. Or how many of you are comfortable in decoding this expression after spending some 20 to 30 minutes of time? Of course, it takes time to decode you know what this expression is actually doing. We have to decode it for the first time. So once we understand the computation, then just by looking at the expression we can recall what it is actually doing, right? Okay, so I see that people are struggling with these kind of expressions. So since in deep learning we often visit this sort of expressions, it is better to, so I just thought of covering it right now, so that when you both in theory as well as in practice, when you deal with dimensions, you feel at least some sort of comfortness, okay, to carry out some operations across different dimensions. Okay, so that's the intention of this 15 to 20 minutes of um, you know this topic. Okay, so just I would like to cover that. So what is the first step, or what do you tend to do if you want to decode this operation involved in this expression? What will be your first step? I just want it to be interactive. You are just encountering this expression. What do you do at the first attempt? Why that is an absolute silence? So it's just an what do you tend to? That's what I'm asking.
So, I mean, for me, it looks like, of course, I see ij. So, I'm calculating for a particular value of ij.
Hmm.
Um, so, I don't know if it's I row or j column, but for x and y, we are fixing those indices for I and j. And then we are taking combinations of L and K, right? So there's an yeah, L is going from something to M and K is going up to C.
Yeah. Okay. So of course, after you write down all these nuances, right, you substitute some values for CMN, and then you try to get some idea about what is being computed. Okay. Uh, I hope each one of you could come up with your own way of doing this and finally figure out what this expression is actually doing. But I want to give you some general framework. Okay, I won't even say it's general, but that's what I follow. So let us, the first step, right, that we need to do is that we have to look at the dimensions involved. Okay, so I'm seeing that C is a element and there is one dimension I and j. Okay, two dimensions I and j, and I in the right hand side I see, in all these three cases there are two variables x and y, and each of them have three dimensions. Okay, of course, for x it is, maybe I can write. Okay, so in each case I can see there are three dimensions involved. Okay, I'm just counting the dimension, I'm not looking at the notations. Okay, so but for x I have ilk, for y I have ljk. Okay, but anyhow it is just three dimensions. So one thing is that when we are dealing with two or three dimensions, one better thing is that we can start visualizing it. Okay, but when it goes to fourth dimension and visualizing it is quite difficult, but since it is three, we can visualize this. So we can visualize this as a cube, right? And being, we are already comfortable with this matrix notations, I for rows and j for columns. And then now there is a third dimension, that is k for depth. Okay, so we can follow the same I, j, and then k. Okay, these are running indexes. First thing is figure out the number of dimensions involved. The second thing is how many indices are there. Okay, and generally it is not necessarily number of indices are equal to number of dimensions in all the computation. Here we have four indices I, j, k, l. Okay, and if you carefully look at this expression, you can see we are using L for column to denote column in x, and we are using same L to denote row in y. Anyhow, we are using same letter to denote the different dimensions of these variables x and y. Okay, so that's what, once we figure out this number of dimensions and number of indices, then next step is, okay, typically we can ask this question, what are all the functions of inside the summation, I and j are kind of fixed, because for each I j we are computing something. So I and j are fixed inside the summation. Only thing varying are l and k, so the summation is over l and k. Okay, so we look at this, and then now we have input. Both the input x and y are of three dimensions, and the output is going to be two dimension I j, just I and j. Okay, so when we have a single index I, which means we are running over some arrays. When we have two index that vary I and j, if we vary I from some 1 to n and then j from some 1 to n, we are varying, right? So when we have two such indices, then we are just doing something, kind of matrix. We are, the elements belongs to a matrix. Now we have ijk, then the element belongs to a three-dimensional tensor. Okay, this general thing. Then yeah, so again, trying to visualize, if possible, wherever possible, trying to do some sort of visualization is always helpful. Okay, then yeah, the output is going to be 2D. So once again, we follow this I and j notation, and the output, each element in, to compute each element in C, we have to use this formula. That's what the expression denotes. Okay, then we have to look at how the computation is actually carried out. It is always, once again, good to put some values for, because for each element we are just going to recursively compute this formula by just changing the indices. So let us put some value for I and j. Typically you can take any interval, but I take some value. Yeah, before doing that, remember, for x, this is a tensor belong to x and this is a tensor belong to y. Both are of three dimensions. And here for x, I denotes the row, okay, and j denotes the column and k denotes the depth. you look at the position of these indices. Okay, and for y there is a switching. Okay, so same, we are using the same index. For x it is for column and for y it is for row, but if we have more than 3 dimension, we say it is I 0th dimension, L first dimension, something like that. Okay, so here I'm just using this terminology, row, column and depth. Okay, so the moment we know this, we can see some sort of, because we are switching the rows, so there must be some sort of matrix product or matrix vector product or whatever it could be. But let's run over. Yeah, single. Please ask your doubt.
So, like sometimes is it like possible like we write depth first and then we follow it by row and column?
Sorry.
Like sometimes we just do depth first and then we pick a row and column. Like sometimes is it possible to put K L J instead of
Yeah,
L
yeah.
J K?
That
So
is
order
absolutely
doesn't
fine.
matter.
Yeah, yeah. Because now we are considering we have to be consistent. Okay. So
Mm.
whenever we create some tensor, we have to be consistent. So typically, it is always going to be 0th dim, first dim, and second dim. So here we can't interchange. Uh, so I could understand your question. So in practice, if you want some sort of real world example, typically in deep learning, the depth is, when we take a batch of samples, people either put the batches in the 0th dimension or in the last dimension, but they have to be consistent across the entire operation. You can't switch the dimensions in the, intermediate computations. As long as you are consistent, you can follow whatever you want.
But here we know that K is the depth because K is same in both position. Like so
Yeah, yeah,
that okay.
that is true. You can't write xkil and then yljk. So
Mm.
that kind of becomes inconsistent. Okay, so let me finish this. Okay, where I was. Yeah, now we recognize all these, you know, we are clear about the indices IL or IJLK. So what it is actually. Okay, so let's fix the value for IJ for C. Okay, and again I put some kind of, fixed values, because I know the same thing is going to be repeated for each values of I and j. So once if I understand how this right hand side equation is computed for single value in C, then I can repeat the process for all the rest of the values. Okay, um, now we have k as well, so I fixed I and j, and also we have k, so let's fix k as well. So the moment you fix k, what happens is that you can safely, truncate or just remove this outside summation, because we fixed it, and then you can rewrite the terms. Okay, so because we fixed all this, you can kind of get rid of all this and then just look at this. So if you are well versed, if you are already good at recognizing the dot product or matrix vector product just by looking at the index, it is good to go. Okay, so by just looking at this interchange of rows, I mean L in their positions, one could immediately recognize this is a dot product of x and y. If you are not able to do that, then you can just go ahead and see what is really happening. Okay, so the next step, now we have to vary the L. Okay, so I have to vary L. So once again we fixed I, I is equal to 2, which is I for row, I mean 0th dimension. So this is running from 0, 1, 2. Then I fixed I is equal to 2. Now we are varying L from 1 to M, or whatever the to the entire value. Okay, which means we are taking, or we are taking this slice. Okay, and similarly we fix j is equal to 2. Okay, which is actually the first dimension for this y. Okay, and then we are L now is for 0th dimension, so this is going to be, and again, a vector of same size. Okay, so x is of size M, and Y is also of size M. Okay, and we know that what we are doing is we are just multiplying element wise, and then we are taking summation. So you can safely write this down as a dot product. Okay, so we know this already. So what happens if I change k? If I change k from 1 to 2 and then I repeat the same process. Okay, so still now we haven't computed C to 2. We are still computing C. I mean, this value for this element. We have just computed one row vector, one column vector. Now I have to move along the depth as well. So if you move along the depth, then for k is equal to 2. Oh, okay. Yeah, so for k is equal to 2, we just move along depth for x. Again, we move along the depth for y as well. Okay, so if we simply repeat this process along the depth, so which means we are simply extending this dot product along the depth. Okay, so finally we end up, if you substitute k from 1 to c, finally we end up dot product of vectors along the depth. Okay, or if you still expand this, you can see that what we can see is the dot product is simply element wise product and then summing things up. So all these things will be, it's like we take this slice, the matrix slice, and then this matrix slice, then we simply multiply element wise and then sum it up. Okay, so that's how we compute single element. So for each element, so if you want to compute this element, then what really happens, you take this slice and then this slice. Okay, then compute this. So now the entire operation is kind of simplified. Ultimately, this formula just simply denotes that we take a matrix along particular dimension of compatible size and then multiply element wise and then sum it up. Okay, so that's what really happening. So why this is helpful is that often in one thing is you could understand what is going on by looking at the formula. The other thing is that in often in PyTorch and in any deep learning framework, we kind of deal with multiple dimensions. Okay, where we need to carry out different types of matrix multiplication or matrix uh, vector multiplications. Okay, so you can vectorize it instead of writing for loops. Okay, even you instead of using slice, there are some functions in PyTorch like something called as batch matrix multiplication, where you need to be extremely cautious when you want to multiply matrices. Your ultimate aim is to just multiply matrices, not cases like this. You want to multiply two matrices, but the matrices are stacked in batches. Okay, so in such a case, these sort of things will really help you. And when you encounter here, it is simple xy, but even if I can make it complicated, right? I can put the derivative here, I take f for some function of x. It could be any complicated function, but ultimately if you decode how many dimensions are there, if you just count number of dimensions and number of indices, you can visualize all these operations as some sort of matrix or tensor multiplication. Okay, and then this will really help you to understand a lot of concepts. It is not actually scary once if you know finally realize that all these are just matrix multiplication or tensor multiplication, nothing beyond that, just written in terms of these equations or expressions.
Okay, a quick question, Arun.
Yeah.
So here it is all 3 by 3 by 3. So I'm in a train. I'm just asking it quickly because now it is stopped. So, but the dimensions, some of the dimensions could be different, right? So you just for convenience, you put it all 3 by 3 by 3 here.
Yeah. So just for as a simple example, I took this case. You could change the dimension, but if it is a matrix vector or matrix multiplication, the size has to be compatible. A lot of times, when you use this batch matrix multiplication function from PyTorch, it throws an error stating that the dimension is not matching at particular dimension mismatch, something like that. So Yeah, in such cases we have to ensure this compatibility between the dimensions.
But see, the depth could be not 3, right? Obviously, I and L have to be, I and J have to be compatible. I understand, because you are doing the multiplication. The other
Yes.
dimensions could be 4 or 5 also, not necessarily have to be 3, right? I
Yeah,
mean,
that is
the length of the dimension or the size of the dimension.
yeah, it could be kind of rectangular matrix. uh, and also when of course in the later weeks, when you implement something called as or an recurrent neural networks in practice, when you do it in practice, you have to once again do some sort of broadcasting across some dimension and pad the elements, with zeros. So all these things happens along the dimensions. So I would say, make yourself comfortable with manipulating dimensions of tensors. Okay, manipulating in the sense not just um, doing some sort of operation between tensors, it is also accessing elements across a particular dimensions. Okay, slicing elements along diagonal or something. you you make it as a, I would say, as a game. Okay, you create tensor and try to access the elements and understand how the dimensions works in particular framework. It is standard across all the frameworks, but you choose the frameworks of your choice and then just play with it. This will help you really a lot when you are implementing a project. Okay, even if you want to do some sort of research, oftentimes you end up writing your own code to carry out some multiplication operations, okay, from the scratch using a core operations. In such a case, it is really helpful. Also, to understand others code, people tend to write, this, they always vectorize all the operation and write equation using those operations. Okay, so this is what I wanted to cover in this session first, so that anyone watches this in the YouTube, also please do try to understand all these operations. Okay, now if you have
So,
yeah, I think two of you simultaneously talked. Um, yeah, Srinivasan sir, you can go ahead. I see in this course people are asking for the solutions, and once again we are determined not to share the solutions. So we hope you solve the problems, got the solutions, and you keep it with you for final revision, either for quiz or in quiz or whatever. So if you are get stuck at some point while solving the problem, please post your steps. Then I try my best, or any fellow students could try their best to answer your questions.
So I have a doubt in week 2 GA.
Week?
2 GA.
Yeah, please go ahead.
So there is this
Uh,
question involving bias there.
okay, let me share the question by the way.
yeah, okay. So, Parthas, sorry, Parthas.
Yeah, your voice is slightly breaking, Srinivasan sir. Is this only for me or to everyone in the meet?
Everyone.
The quiz is actually in the next week, right? It's nearby. So I hope you are all started preparing for quiz. Yeah, what is the question number part?
It's question number third. So I'm
It's
unable
like
to understand in this question, like how setting the bias to any of the four values makes the network work.
what I'm asking here. Suppose that we use them to implement a Boolean function which has the following truth table. Which of the following will be not? This will be not. Bias for bias of the perceptron in the output layer is or valid. Using suitable threshold function. So what I'm guessing is that so we are talking with respect to bias of output neuron, right? And
Yeah.
I have given some configuration and also weights are fixed. And what is that W1 and W2? So what I believe is that if you write down the expressions for W1 and W2, I mean all the expressions for this output neuron explicitly, um, and also suitable threshold function. What is that threshold function? Okay, work it out and get back to you first because I also need some time to think what I asked here.
Okay, so should I post it on Discords?
Yeah, please do that so that when I look at it, even if I tend to forget that, if I look at the discourse, I can recall and work it out.
Okay, I'll do that.
Yeah.
So same week two, practice assignment one. So practice assignment question number one.
Mm,
Same week two.
this one.
This, I mean, this is still this. I mean, this concept still confuses me in terms of how many regions it is splitting into these neurons. Because for a XOR function, in some other question, we have split it into three regions, whereas in this, the answer seems to be two regions. So I'm
No,
confused usually how to.
the thing is that so the way to think about any sub, especially when it comes to kind of splitting the region, all these things. Let me share the whiteboard. So be it our function. Okay, is the whiteboard visible? I'm writing something on the whiteboard.
Yes, sir. It is.
Okay, so no matter what function we have, right? There are n infinite number of Boolean functions, but we know that the output is either going to be only two states, 0, 1, or -1, +1, or whatever. So we have only 0 or 1, right? So no matter what my input is, all these inputs are either classified as 0 or 1. So which means my space has to be, there is only one way. The entire space has to be divided into two halves, right? So if you implement XR using some network, okay, it could be even not necessarily perceptron, it could be neural network or whatever, and despite my input, my output is always going to be 0 1 case, okay, either 0 or 1. So ultimately your space is going to be divided into only two spaces, because even if your intermediate layers divides the space into multiple regions, the final output neuron merges all together and it will end up with only dividing this space into two halves, which means we have only two space, one for label 0 and the other for label 1.
Sir, but if you look at the same question number three in the same thing,
Okay, let me switch.
in the practice assignment itself.
Ah,
So it's that's also an XOR function,
yeah.
right? And there it is splitting it into three regions. So it's the same 0, 1, but because it's an XOR function, it's split into three regions, right?
No, only two regions, right? One region for 0, the another region for 1.
Okay, so you're talking about okay. So it's not that even though it is actually drawn two decision boundaries and combined the function into two,
Hmm.
it's still two regions. One is green and one is white. Is that how you're saying? You're saying? I mean, it's effectively made it into 0 and 1.
Yeah,
0 or
that's
1.
what I'm saying. Even if you use some sort of neural networks, right? The
Right, right,
intermediate layer divides the regions in some multiple ways, but ultimately it's a binary classification. So the
right,
region has to be only, there are only two possible regions. Even it could be non-linear region. It could be circle, and outside the region is, typically you might have seen something like that in
right.
non-linear regions in neural networks.
Okay, okay. So that's okay. That's what it means by two regions. Fine.
Yeah.
So if it's not a binary classification, let's say it's a multi-class classification, let's say 4 classes or something like that, then it'll be that many number of regions. Is that
Yeah, typically something like that, but it also depends on how we implement multi-class classification, right? You might have learned about this one versus rest.
okay, okay, okay. I understood. So if it's a simple softmax kind of a function, then it's not really drawing linear boundaries. That it's just calculating probabilities and taking the highest.
Yeah, some sort of boundaries are there. It has to draw some boundary, but I don't know if we.
It's not linear. It's a linear.
Yeah, it's not going to be linear boundary. Yes.
Right, right. Right. If it's one versus rest, then it's probably more like a classification. I mean, binary classification.
Yes, yes. It is. If it is one versus rest, yeah, you will have a lot of boundaries. One
Right.
versus one, no. One versus one will have a lot of boundaries, I guess. If I don't know, I'm not exactly
Right.
remember
Right.
the
Right.
differences, but
Hmm.
okay.
Okay.
So for
I
quiz
was
one,
yeah. Sorry, go on.
yeah, I was just telling for quiz one, the syllabus is kind of from week 1 to week 4 contents, which means from, of course, you don't need to bother about the history. No questions will be, no historical questions. You can skip the first half of the lecture. Don't need to focus on memorizing any facts. You just start from perceptron, basic NP neuron, and then perceptron, and then all this um, representation of approximation of any function with sigma neuron, and then single sigma neuron, and then neural network, and then these basic optimization algorithms, GD, momentum, and MAG, and also the different types of, what is that, the different way of training a network using batch or mini batch or stochastic, and different types of learning rate schedulers. And if the formula is too complicated, don't try to remember. We give you the formula. I hope in any of the weeks we don't have much formulas, but even for perceptron, it is simple to remember. It's not that much hard to remember the perceptron update rule. But for the rest, you are expected to know how to compute the gradients for sigma neuron. Even if you have interconnect more than one sigma neuron, then how do you compute the gradient? Okay. And also you should be able to compute the gradient for a simple neural network. As in the case of week 3 assignments, you will be given a toy neural networks, so you can refer to the previous quiz questions. In all the, if you look at the questions, the pattern is that you will be always given with some simple examples. Okay, because of the time constraint in the examination, we ensure that anyone could able to compute all these sort of matrix vector multiplication in a stipulated time, and be extremely cautious. Yeah, we will I will say all these hints and tips in the next revision session, but I'm just telling it right now also.
So what is the difference between learning rate schemes and learning rate schedules?
Learning rate schemes and schedules. No, only the difference comes when you whether you are adapting the learning rate or just scheduling it. Scheduler. Can you tell me where you are actually seeing this definition? Is it in there in the lecture?
So there are two lectures named. One is named like scheduling learning rate, and another in week 5 that is learning rate schemes. So from there,
Okay. Uh, I'm not remembering the exact differences, but what I see is that learning rate schemes means, I mean, it's an umbrella term. All different types of schedulers, adaptive schedulers, everything will come under this single umbrella term, learning rate schemes. But personally, what I see the difference is, if your learning rate is adaptive, then that is different. If you schedule I mean, if you have some exponential, we have different types of learning rate schedulers, right? Something you exponentially decay the weight and doing line search. I don't think there is a concrete differences between these two. If I come across the exact definition, then I share it.
okay. And one more question: how sensitive does like a model's convergence get with the batch size? Like get how like having a very low batch size, would it make the model converge like very slowly or not converge at all?
Yeah. So once again, there is no theory. So, but by looking at the examples, right? If you are giving SGD, then the model's loss will oscillate very much, but an average, it converges. That's what we see. If you increase the batch size, the model converges quickly because it is computing the gradient and also moving in the right direction, but it takes a lot of compute. So that's for sure. If you are increasing the batch size, then the convergence, you can expect the model converges if there is some sort of local minima. If you initialize the parameters to a same set of values in all settings, then we can see if you have a lot of uh, you know data points, then the model converges quickly. So even in the bonus activity questions, in the assignment 2 of bonus activity section, we are just experimenting with that. Increase the data points, see how fast the model converges, reduce the number of data points, and see how long it takes for the model to converge. Having more data points is always better,
Okay.
but there will be a problem in terms of computation memory requirement. That's why we go for batch gradient. Sorry, mini batch gradient.
So like having a higher batch size won't affect the quality of weights I get. Like having a lower batch size won't affect the quality of weights I get.
Quality of weights in the sense,
Like quality of weights, basically like the quality of the model, maybe
quality. So if you look at the
based on the loss.
trajectory, right? Yeah. So what here we can kind of compare using trajectory followed by these three different algorithms. So if I use GD, let's say I have trajectory 1. If I use mini batch GD, then I have trajectory 2. Then if I use SGD, then I will have different oscillating trajectory. But there is no guarantee all of them will converge to the same point. They will end up with different point. One thing people observe is that oftentimes, in terms of quality of convergence, SGD is better. The reason is that in deep learning, the loss surface is highly noisy. I think we discussed about this a bit in week 6, where we talk about regularization stuff. So when your loss surface is kind of noisy, which means you have a lot of ups and downs, a very small ups and downs. Typically, GD stuck at local minima. That is very bad local minima. but SGD has this tendency of overcoming these short ups and downs and eventually end up with some better local minima. All these are kind of empirical evidence. Again, unless we have a theory, we can't guarantee this is always the case, but empirically SGD ends up with some better minima than GD.
Okay, so thank you.
So, like just like momentum based gradient descent always give a smaller loss value as compared to GD at the end.
Sorry, which one has smaller noise value?
Momentum based gradient descent, is it like smaller value than gradient descent or same like loss value?
Smaller value in the sense I don't
Like
get it.
it does momentum based gradient descent give you a better accuracy at the end, like reducing converging to a better place, like reducing the loss to 0.001 and gradient descent like maybe conversion to 0.1 only. So like this momentum gradient descent gives you better loss value at the end.
Okay, so when we talk about convergence in terms of loss, where we assume zero loss means the algorithm converge. So again, we have to first consider what sort of loss surface we are talking about. So if it is convex loss, then it doesn't matter whether, of course, using momentum help you reach the loss of, I mean, the minimum point quickly, and maybe there might be some oscillation. So all, whether it is GD or mini batch GD, sorry, batch GD or momentum or NAG, will end up with the same minimum point. But in deep learning, that's not the case. It's not purely convex. So there we can't even say momentum always gives you a better, what is that? Not accuracy, but in terms of loss, we can't say momentum always gives you a better loss than GD. So the core reason why we go for momentum is that GD can stuck at some flat region, so you have to run the algorithm for for more number of iterations, whereas momentum could overcome that. Oftentimes we again, it's empirically, no matter which experiment or domain you are working with, you can see that at some point GD moves very slowly, which means it got stuck at some flat region. But momentum help you, reach the minimum or reduce the loss quickly by converging fastly. And one fact that I just recall now is that why does it matter? Why don't I just run the algorithm for some 100 more iterations? Does it really matter? Why I could just run it for one more day, right? So in that case, the answer is that for really big deep learning models, even running the entire model for one iteration costs you millions of dollars. Let's say GD converges in 10 iterations and momentum converges in 8 iterations, then you save $2 million. So that's why people are focusing on these type of different types of optimization algorithms. So it's not about the quality of convergence. It's very difficult to talk about the quality of convergence in terms of optimization algorithm we use. It is all about how fast the algorithm converges.
So we like made we had gradient descent, but we made all of these the gradient descent algorithms because of speed only, right? That's the only main reason, not
Yeah,
the
yeah.
accuracy.
Yes, yes. Faster the convergence, there are a lot of advantages you have, especially for deep learning models, not general machine learning models, but for deep learning models.
And like I have question regarding sparse features. Like how can a sparse feature ever be important? Like even if we consider that sparse feature, like what change will it make? Will it increase the accuracy by like 1%? Like what does it do?
Sorry, could you rephrase your question? So we have sparse features, okay.
So suppose I have one column which is like sparse totally. So if I include that sparse feature, like what change will it make in my accuracy? Will it increase it by 0.1% maybe? Like it won't matter much, right? How do we define if it's that's an important? Like how can sparse feature be important?
Okay, so if I understand your question correctly, let's say I have some sparse features in my data set, and then I use GD to train it, um, or I use this adaptive gradient based algorithms to train it. So what advantage do we have by choosing these two different algorithms? That's what you're asking.
Mm.
Yeah, so ultimately, once again, it is faster convergence. In the toy examples, right? So in the lecture, we used some toy setting. There you could see that if there are sparse feature, then uh, the trajectory of the optimization algorithm, right? It is actually very long, okay, because it is moving in one particular direction all the way for first some n iterations, then it takes turn. Whereas the adaptive gradients, what happens is that it moves in a short distance, okay, again with respect to the toy example, which is some sort of diagonal distance from the first few iterations itself. So we are just preventing the algorithm, right, by moving only in a particular direction for a long number of iterations and then take turns. So we want to reduce that, which means we want the algorithm to converge faster to the local minimum. So all these adaptive gradients are really helpful, especially when we have these sparse features, like in the case of image and text.
Sometimes like these sparse features cannot be important, right? Like
Yeah, if your data, in some cases we can't avoid sparse feature, we can't eliminate it, as in the case of text and images. Let's say I have an image where the object is white in color and the rest of the background is black. So if I reduce the size of the image, still I have these black pixels, more number of black pixels than white pixels. So I can't eliminate none of these pixels. So I have to deal with these sparse features. So in such a case, if I am going to train a model, then I can choose adaptive gradient algorithms than these just plain or vanilla gradient descent algorithms. If you
just
could drop the sparse features, then that's good. If you think this sort of feature is sparse and we don't need that, because oftentimes it is sparse features that carries more information than the rest of the features.
but for example, like if we have a data set and we have one sparse column, how do we know if it's important or not? Like what's the procedure to know that?
So if you plainly ask this question, that's very difficult. But again, it based on the domain knowledge, you could get some insight. Say, for example, the moment I could recall something related to the document classification. Okay, so let's say I want to classify two documents based on the number of based on some fixed sort of words, and I just count how often this particular word has occurred in a particular document. um, let's say one is historical and the other one is uh, some sort of maybe chemical or whatever. Okay, so some words are very specific to particular domain history and very specific to chemistry, right? So if I count that particular word, it rarely occurs, so its value is very minimal, and for that particular column we have a lot of zeros, but somewhere it is one, which indicates that this single feature can distinguish compared to the rest of features. This single particular feature can differentiate two documents very precisely than the rest of features. So we can't remove this sparse feature there because it is very important. uh, so I just recall the definition id of something, I don't remember what is that, inverts document word frequency, something related to that. So domain knowledge help you to figure out whether it is this sparse feature is helpful or not helpful. That's all. With that's these things are possible if you are dealing with some specific domain and if you have domain knowledge. If you don't have, then I don't think it's possible.
what if we train the data with the sparse feature and then without the sparse feature, and then we compare the accuracy?
Yeah, we can do that, but for deep learning, that's not affordable. That is oftentimes prohibitive because the compute cost is so high. For machine learning, traditional machine learning, where your data size is very minimal and it doesn't take much compute, then you can play with it. But in deep learning, that is oftentimes prohibitive.
In like a momentum based in Nestor, like they're faster than Adagraph. Like, so what's the advantage of using Adagraph?
Sorry, can you ask this
Like
question?
momentum based gradient descent and Nestor,
Mm-hmm.
both of them are faster than Adagraph. So why do we use Adagraph?
Yeah, so Adagrad is especially used when you have sparse features, right? You could use momentum, there is no issues. So again, momentum, if you use momentum based plain vanilla GD, then again it's move in the same direction, particular direction very fastly, and then oscillate in the other direction, right? Still, it follows the trajectory of GD, but very fastly by accumulating the momentum. It won't take a shortest route.
So momentum based in Nestor like will not take the diagonal route. It will take the longest route at the end. Like it's not recommended for sparse features.
Yeah. If it is, if you observe that your feature is sparse, then using GD or momentum or Nesterov, they all follow the same trajectory. One, you know, travels quickly, the other kind of take a slow steps. That's the difference. So you have to go with adaptive gradients, especially because in deep learning we have millions of parameters. So if your number of features are sparse, then there will be a lot of weights, a lot of parameters that won't get updates. So that actually really painful if most of the parameters are not updated even after some thousands of iterations. So that's why these adaptive gradients are really important when you scale it up. Okay, in all the lectures we just talked about these important concepts with the help of toy example. But if you have some questions, you just think about scaling it up to some billions of parameters. Why it is helpful? You think from the billions of parameter model.
But okay, so if I use Adagraph for sparse features and if I try to use momentum based in Nestor also for sparse features, will Adagraph be faster in sparse features case? Is it?
Yeah, not Adagrad, Adam. You let's say Adam, because Adagrad also tends to slow down after some n number of iterations.
So there's not much use of Adagraph, like basically
Sorry, based on
not much use of Adagraph. Like it's better to
yeah.
use
Now it
Adam.
is Adam or Adam W, not even Adam. So there are other constraints as well. Why in Adam is preferred over an Adam is because once again storage requirement, all these things. All this we have different types of algorithms because one is convergence, how fast it converges. The other constraints are memory requirements to store the gradients, to store the different states of optimizers. Let's say I have billion parameters, I want to store all of them. So for each parameter I have to assign 4 bytes. You just calculate it. Okay, so to compute the gradients I need to multiply 10 to the power 9 into 4 bytes. If I use Adam, I have to store the gradients, I have to store this moments empty, and also square of the gradients. So it simply occupies lots and lots of memory. So these are all the constraints that these are all the factors that we have to consider before choosing a particular algorithm, especially for deep learning.
Got it. And so like gradient descent, like when we do gradient descent and there's a lost surface which is like very steep, then is it possible that gradient descent also shows oscillations just like momentum based in algorithm?
Yeah, definitely possible because there is a learning rate, right? So
Yeah.
we still learning rates. If you're not setting the learning rate properly, then you can see it could oscillate back and forth. It not even converge to the minimum. So in the applet, I think in the GeoGebra applet, in the first setting, if you play with that, you can see for particular value of eta, the GD never converges because it oscillates back and forth between the or around the minimum. It never converges.
And so, like, I have just one doubt in slides about Adagraph.
Hmm.
So,
You want me to share the slides?
yeah,
Okay, give me a second. So Adagraph, right? Yeah, here it is. Yeah, tell me. Oh, forgot to share.
so
Yeah, give me a second. I'm
question
sharing.
5 part 2.
This one. This is orange.
Yes,
Oh, sorry.
slide number 3.
Slide number 3. I think you can directly go there. Hmm.
In this, in VT, like, why are we squaring the gradient of W? Like, why can't we just take the absolute value of it?
Yeah, that's a good question. So, if you take a look, one is we want the gradient to be positive. So, you can think from that perspective. So, if that is the perspective, then we can ask, why don't I just take absolute value? But if you look at the actual derivation of this entire Adagrad rule, okay, so if you look at the paper, this squaring of gradients comes naturally because of manipulation of or because of the approximation of the Hessian matrix. It's like initially this Adagrad is proposed as an approximation second order approximation to the second order. We are computing gradient. If we compute the uh, second order derivative, then we call it as Hessian, right? But computing Hessian is uh, numerically unstable and also it is quite expensive than computing the gradient. So people thought that why don't we just, of course, for a lot of reasons, why don't we just use this approximation of the gradients? So this approximation of a gradient is like you have a gradient vector, and then you just take an outer product between this gradient vector. So you will end up with a matrix where the diagonal elements are all square, gradient square. Okay, and from there they approximate this formula. So it is a natural consequence of manipulation of the equation. So that's why we have this square of the gradient. But if you ask me, can I use absolute value of the gradient in order to compute this Adagrad? You can definitely use, because we are just accumulating the history. We don't want to, in that case, you can accumulate and then still you can use this Adagrad. But in terms of convergence, I don't know how it actually behaves.
But
You
so,
can't
like,
give,
why do we have to make it positive? Like,
sorry, why?
why do we need to make a gradient of WT positive? Like, I said absolute value, but what if I remove the absolute value and I just take WT? Like in the previous algorithms, we're not taking absolute values, we're just taking uh, derivative of WT. So, like, what, like, does it matter that it needs to be positive, or
Ah, uh, there is an insight to it. You just think about it. What if I allow negative values, or if I just consider the value as is? Okay, just have a gradient. I just accumulate just the gradients without squaring it or taking absolute value. Just use as is. That's what your question, right? Yeah, I want you to think about that. What really happens? Why we insist on using these positive values? What happens if we just use that as is?
And so, like, why do we use epsilon in the like denominator? Is it for like zero cases, like or infinity or something?
Yeah, so it could be possible, right? At some point, my square root term, or even during the initial iterations, it becomes uh, 0, right? So we ran into this in or undeterminate form, indeterminate or 0 by 0, something like that, or 1 by 0 that becomes infinite.
What's the recommended value for eta? Sorry, p, like epsilon. Like, is it like 0.1? Anything you can take. Doesn't matter. You have to take a very small value, basically.
Yeah, basically very small value. Typically, it is 0.40 and 1, 0.0001.
And so, like, in this say that W vector is the sparse feature and V is dense. Is it always the case that W will always be sparse? Because it depends on X.
Sorry, W is not a sparse feature, right?
No, but
Are
like they say, like it's sparse. Like X is sparse, but they consider W and V, and they
you,
say W is sparse and V is dense. So it
no,
moves
you
in the
can't
direction of
say that, right? So because W is initialized to some random value, it's not necessarily 0. So if we initialize it to 0, even at some iterations, it gets some value, right? It won't remain 0 always.
it. Like slide number 5, it's written this line.
Okay, let me see that. Oh, slide number 5, you mean?
6, oh sorry, 6. So here it is said this of in the second paragraph.
Mm. Two parameters W and B. Of these, the input feature corresponding to B is always on, so
And,
can't really make it sparse.
and then if you come to slide number 9, uh, then
Slide number 9. No, here first, let's
the
understand
second
this
paragraph,
one.
yeah, this one. On the other hand, B is very dense and undergoes many updates.
B is
Dense and W is sparse, it says.
okay. The future corresponding to W, the future corresponding to B. I think it should be interpreted in that way. The future corresponding to W is sparse, and hence W undergoes very few updates. On the other hand, it's like the future corresponding to B is very dense and undergoes many updates.
But
Maybe I add
feature, but
the
feature
future.
will be similar to W and B. Like,
Yeah, we are talking about the future corresponding to W and B.
they would be same, so how can W be sparse and B be dense then?
No, why should be for the future for B is always 1, right? So it is always dense.
Because it doesn't depend on X.
Sorry.
Because feature for B doesn't. What does it mean for a feature for B basically? Like if you see the derivation, like sigmoid function gradient derivation, we get
Mm.
like fx minus y in that big equation. So in that we have x and w, like it multiplies with x. That's why we say that w depends on x. So that's why we can say that if x is sparse, then derivative of w will be sparse. But b does not depend on x if we see like the sigmoid function derivation. So
That's not actually W, that's the gradient of W, right?
the gradient of w, yes. So like I didn't understand like how they are related, like how like why is it called sparse and why is that dense and
No, W is okay. So you just think about it deeply. So you, whatever the case that you listed out here, right? So I would say in such a case, what I do personally is that I take all different 4 cases and write it down explicitly and look at the equation and then come to a conclusion. So why this is defined in this way and why this is defined in that way. But here what you are pointing out is maybe I have to add this with the future corresponding. I have to copy this and paste it here. On the other hand, followed by the future corresponding to B is always 1. So we say it's dense. That's why it
Why is
undergoes many
always
iterations.
one?
Yeah, B is always 1, right? It's corresponding to, it's a bias term.
So it will always be dense then, like in every situation.
Yeah, B is not dependent on any of the features, right? It is always going to be 1. It depends on the difference between the loss and the sigmoid function, all these. That is also the gradient of B, not the B itself. Okay, so any others have any doubts? So you are staying silent just for listening, or if you have any question, you can ask, and then I switch back to single.
Sir, I have one just general question based on some graded assignments in the past, but this for all practical purposes of the exam, you're going to treat the for perceptron the linear equation the equation for the linear boundary, right, is going to be w1 x1 plus w2 x2 minus w naught, right? It's not going to be plus w naught anywhere,
Yeah, so I
or will
see
it be
this.
explicitly said?
Yeah, so this seems to be a source of confusion for many.
Because there is one assignment where that question kind of, because the equation for that was taken like that. So if you look at graded assignment 1 of
Yeah, so yeah, that's right.
question number
So
7, yeah.
Question 7.
okay. So anyhow, without even looking at, so this causes trouble when we switch from MP neuron to perceptron, right?
Yeah.
So somehow in MP neuron we keep this W naught here as a threshold, right? So if I ask you what is the value of W naught, it simply contained in real number. It could take any value,
Right.
any real value, right? So when we compare this, especially when we make, uh, it's like we set the threshold to always 0, and then we bring in some sort of features here.
Yeah.
Okay, so when we say perceptron, when we explicitly write equation something like, we consider W naught as a bias term. Once again, so in the question, if I have just given you W naught is equal to 1, right? Suppose in the question, when I return something and say W naught is equal to 1, so it means you are asking whether I should put, whether I should consider minus 1 here, or entire minus
Just
W naught
add
is
one.
equal to 1 here, right?
Yeah, correct.
Okay, so in
Also,
the,
more importantly, in one of the questions in graded assignment, what's happened is the inequality itself is framed based on W naught being just a positive number. Like it will be like W1 x1 plus W2 x2 plus W naught is greater than or equal to 0. Because we have treated x naught to be 1. So W naught plus x naught is greater than 0. And the inequality just solves based on that. The answer is based on that. So if I use minus W naught, then the inequality doesn't work out.
okay, so I see the confusion. What is that question number?
So it's a graded assignment 1, question number 7.
Oh, graded assignment 1. Okay.
Yeah, so it's basically a NAND gate, NAND gate. And if you look at the question,
Question number 7, right?
question number 7.
Okay, the dependable should NAND gate, suppose that also.
So it says the bias control is strictly positive. That's the answer that's given. But then I won't be able to get that unless I treat W naught as a positive number.
Okay. Yeah. So this question needs more clarity, yes. Okay, I should
So
have given the
precisely.
decision rule. That's the better way.
Right.
Okay, in the
So,
exam I use it
so
to
in
give
a
the
quiz, you'll be able to give you that, right? So you'll give us the decision rule, then just otherwise by default, we'll have to assume it's minus W naught, right? That's the meaning. What I mean is W1 x1 plus W2 x2 minus W naught is greater than or equal to 0 should be the decision rule typically, right?
yeah. I have to change that question. Yes, I mean I have to add the decision rule there. So in the exam I do add these decision rules. In wherever I use the
Okay.
questions, I give you the following decision rule is used, something like that, to avoid any confusions. But in that question, yeah, I understand your
Sure.
concern.
No, I think the problem I had was because when I was solving this during week one, I was able to easily answer it because largely the thinking process was from MP neurons.
Yeah.
Then after we have learned week two and three now, when I go back to this question, I'm just confused why I'm not able to get this answer. Then I realized it's actually taking this. So yeah, as long as the nation rule is explicitly mentioned, that will be okay.
Yeah. That suggestion I update the question. Otherwise, I miss it in the next term. Yeah, I mean, in the exam, I ensure that you get the decision rule. So even you solve the previous quiz term papers and see is there any confusion. And
Okay,
if
I'll do
you
that.
see any sort of confusions, just point me out. So I ensure that it won't repeat in the next quizzes.
Sure, sure. So that was my only question.
Okay.
Week five, I mean, I've gone through the content and all that, and in fact, answered the uh, PNG, but I didn't really have any questions on week five directly yet.
Okay. So week 5 it doesn't have any practice assignment, only graded. Yes.
But only, I mean, sorry, on week five, just one just one similarity, or rather, I don't know if it's similar at all. You are kind of looking at, whether it is Adam or Adam Max, so whatever we're doing beta into history plus one minus beta into the gradient, right?
Yeah.
Uh, that looks like a convex function, formula for a convex function, right? Like, is there any link at all? Like, typical convex function would look like that, right? You'll have lambda, x1 plus 1 minus lambda something.
Yeah. So
I don't know
we
if there
can
is
say
any
it's a
similarity.
convex combination of something. So typically, yeah, in convex function, we set some parameter and we ensure theta and 1 minus theta. So they are restricted to take values between 0 and 1.
Right.
We can call it as convex, but I don't think it conceptually it doesn't make any difference. You can think of it as exponentially weighted moving average. But these are all just
Okay.
terminologies, okay. But conceptually, I don't think.
There's any link. Okay.
Yeah.
So it's almost just like weighting. If you treat beta as zero point 0.9, you're giving 0.9 weightage to history and 0.1 weightage to the current gradient. That's all it is it?
Yeah. That's all
It's,
it implies. That's what we can
okay.
conceptually infer what it is actually doing. Some,
Right.
if you maybe when we scale up to some millions of parameters, who knows? So if someone digs deeper, maybe they can come up with some convex explanation for this weight update rule or this history.
Right. Now, suddenly it was just so striking that it looked like a convex function. That's why I was wondering whether it was meant to be like that or something.
Yeah, I got your point. Yes. Okay. So any doubts, single?
Just in the code, like slide number 5.
Okay, then you go back to there. Is that slide number 6 or 5?
5. Slide number 5.
Okay. This one?
Yes. 5. Yeah. Shouldn't this be plus equals to like in grad W and grad B?
Mm, yeah, we are accumulating it, right?
Hmm.
Yes, it should be plus equal to.
And I have just 2 questions left and I'm done. Like, can perceptron be used for regression?
Sorry, I could not
Uh,
hear it properly.
can perceptron be used for regression problems as well?
Perceptron used for?
Regression, like real inputs, real numbers, basically. Instead of classification, we can just have numbers.
Yeah, so if you are using perceptron, right, so it's going to be a linear regression. So only thing that differentiate is that we do use a boundary and then we pass it through a threshold function. So if you don't use threshold function, then it becomes, you could use it for regression, but there we don't need to call it as perceptron. So for historical reason, these are all just mathematical manipulation, right? So whoever invented some sort of thresholding mechanism and then linear for a linear function, they named it as perceptron. So we follow that. But mathematically, it is just adding some nonlinear active function and just a linear decision boundary. So if you remove this nonlinearity, then we have a linear regression.
We won't have any threshold or anything like that. We'll just have some simple bias and we get the answer.
Yeah, yeah.
Like,
Becomes Wx plus b only.
That will just be linear regression.
yeah.
Yeah. So
And
this
so in the practice assignment, week 1, question number 2.
question number 4. Where is that? Practice assignment. The statement that all Boolean function cannot be implemented only using excitatory input is. I think the similar doubt was asked in the first
Yes, like
session.
I understand like that, but like I was thinking of like functions which are non-linearly separable but also Boolean in nature. Like I was thinking of some examples and I come up with that. I just want to make sure that if I'm correct or not.
Okay, so let me understand that all Boolean functions. True for non-linearly separable Boolean functions. True for some Boolean functions independent of whether. Okay, so the confusion was around this point, independent of whether they are linearly separable or not. So I think option 2 was the correct answer, right?
Yes.
Okay, so what was your doubt?
So like I was thinking of some examples like which can be like non-linear and also Boolean and we can solve them. So I come up with an example. I just want to just tell you like just to be sure like if I'm correct or not.
Okay, okay. Please share it. So if you have some whiteboard, something like that, share it, or you can speak orally as well.
Why?
Or you just tell me, I try to draw it.
Okay. I have, but it's very poorly drawn, but I can still show.
Okay, so how many number
So
of inputs
basically,
to the function?
uh, one is 1, 0,
Okay, so you're telling the path.
and then and that and another one is 0, 1.
Hmm.
Uh, so first one gives you 0, and another one gives you 1,
Okay,
and the x1 is the inhibitory input.
so you are telling x1 is equal to inhibitory.
Hmm.
Okay,
Because x1 is 1, that's why we're getting 0.
so it's an inhibitory.
And the threshold I'm using is 1. So x1 plus x2 is greater than equal to 1.
Okay.
So greater than equal to. Uh, yeah. So then when I draw a graph of
Hmm.
this,
Hmm.
so I put 1, 0 and 0, 1 respectively.
So you are considering only
To
two possible configurations.
hmm,
but you have to consider all the possible configurations, right?
But
So when
just
we
for
say
like
it's a
this,
function,
Hmm.
okay, so anyhow, 1 0, okay, 0 1 is here.
now like if you draw the x1 plus x2 equals to 1 decision boundary, it passes through both the points because those both points satisfy this equation. So we can draw this line. But yeah, so these 2 points lie on this line, so that means this graph will classify these 2 points as positive. But according to the equation we wrote, 1 0 should be give us negative output because x1 is the inhibitory input. So so it is not linearly separable, but we have a proper function there. So is that correct? Like this setup?
Okay, so when we talk about function, right? So when I say x1, x2 maps to y, okay. So we are talking in general. It's a Boolean. We call it's a Boolean function, and we consider its entire domain. Right, x1 is from 0 1, and x2 is also from 0 and 1 to be set. So the first thing is that what I'm not sure is that when we define a function with this definition, we can't just consider this subset of the domain, which is 1 0 and 0 1. We still have to tell us, I mean, if this is a Boolean function, you have to also tell me what is the value for 0 0 and
Even
1
if
1
we
as well.
use this, then also I think it will not work. It will not be able to linearly separate it. Like even if we add these points.
Okay, so by the way, the question is about what? The statement that
Uh,
all Boolean functions cannot be implemented only using excitatory input is. Yeah, so the question says, even I'm just confused this thing. In other words, all the Boolean functions okay, so what the question says is that if you want to implement some Boolean function, you have to use excitatory input. That's the
hmm,
statement, right? But it is simply not true for at least one Boolean function, right? Then, so why do you trying to contrive this example? Because we
because
invalidate with simple example. So even if we assign 0 0 0 to all, let's say I come up with some counter example. This is one Boolean function where I'm not using excitatory input. I'm just using, oh sorry, excitatory, not, I just confused. It's an inhibitory, right? Okay, so I have to come up with one Boolean function where excitatory input is absolutely required to implement a Boolean function, right? So that example is not gate. So do you get this point? So what the statement says is that all Boolean function cannot be implemented only using excitatory input, meaning that there are some Boolean functions where you need inhibitory input,
hmm,
otherwise you can't implement that.
yeah.
So one such function is not gate, not Boolean function. Unless you have an inhibitory input, you can't implement that not function.
Hmm.
There could be other functions, but the one we could immediately come up with is this not, which is covered in the lecture. So you can uh, validate this, right?
But I was just validating whether that function is linearly separable or not.
Yeah, that part we had a long debate, not debate, discussion in one of the live sessions. I mean, I don't even remember why I used this phrase linearly separable or not, even in that question. So I was not able to recall the need to use that term. Maybe I have to remove that. So we discussed this in detail in one of the live sessions. Of course, that is kind of, I'm still not sure why I used this term, so I think it's better to remove that linear separability. The thing I wanted to emphasize here is that whether you can correlate this with this NOT gate. That's what I wanted to do, but somehow I added this word by mistake.
But so like I'm able to find this function which is also not linearly separable, but in that actually matches the statement. Like this example, even if you take all the four like you know inputs, they give you uh, an answer which is not linearly separable.
Okay, so this is the configuration you're talking about.
0 1 0 1, yeah, 1 at
Okay.
the end.
Okay, so 1 0, your this one is positive. Let's say 0 is negative. So for 1 0, this is negatively labeled, and 0 1, that is positively labeled, and the other one is 0
0 0,
0 0
which
is
is
negatively
0,
labeled, and
and
then
1 1, which is positively labeled.
positive.
Yeah, because x1 is negative. Sorry, 0 0. Sorry, 0, right? Oh, yeah, 0. 1 1 is negative.
Okay, you are saying it's not possible to, I mean, you need inhibitory uh, input in order to implement this. But by the way, this is linearly separable, right? If you are
Uh,
using this threshold, it could not separate it. But if this is my data points, I can draw something like this as well.
but I'm using threshold 1. So this
Yeah.
is the linear boundary I'm considering.
Okay, so if I draw something like this, if this is my linear boundary, then all the points are separated, right?
But
All this.
according to the
No, when we talk about linearly separability, the definition is that whether we can find a line that separates all the positive points and negative points. So now it becomes linearly separable. If we use this threshold, of course we can't, and of course we don't have weights associated with it because MP neuron simply prohibits that. So if I use, what should I do if I want to get this line? So either it has to pass through the
weight
origin.
update.
Okay, so anyhow, it becomes linearly separable. So if I use this word linearly separable or not, then I'm implying, generally it is implied whether you can find a linear boundary such that it separates these data points. But if you ask the question whether it could be found by MP neuron, then we may need to think about that. I mean, we have to find the threshold for it. We can solve it quickly by using this, by solving this nonlinear equation. Otherwise, uh, mhm. Okay, do you get the point I am trying to make? This one is should be less than 0. So this is a conflicting thing, I guess.
Mm.
X1 should be less than 0, which means negative. X2 should be greater than or equal to 0, and x1 plus x2 should be less than 0. Addition of this. So let's say I have number. Okay, maybe give me a second.